Okay, this video here is going to compare the graphs of a function f, its derivative f prime, and its second derivative f double prime. And you can see that I have here in red, this is my original function f of x. It's just a third degree polynomial function. So you'll see again here it has a local max, a local min. And we're going to kind of see how that all ties together with the derivatives and where this function's increasing and decreasing and so forth. And so with that, I have some stuff turned off over here so the graph isn't all that cluttered. But what I want to, I guess, get out of this one here is I trace along here, and you can see that I have this point highlighted here. As I change A, it's just going to kind of scroll along the line and evaluate the function. Here it's evaluating it at 0.1, 1.3, and so forth. Okay, so you can see that I'm just tracing along that function here. And the blue graph, even though I didn't, I could, take this function here and calculate its derivative. So it'd be 3 times 1/3, and the coefficient would be 1, and the exponent would be second power, so it'd be x squared. Same thing here, minus x minus 6. And that's the graph of the blue function, that parabola here. And I really didn't have to compute it in Desmos here. We could just enter in f prime of x, and it's going to graph the derivative. I also have that derivative evaluated at wherever that point is. And so what you see here is that wherever this function is increasing, and I'm just going to kind of click on here, you can see that at -2, it's one of the nice features. And if I can turn that function off for a second. One of the nice features about Desmos is that you can click on Extrema and it'll find it for you automatically and highlight it. So you can see I have a relative max at -2 and a relative min at x equal 3. And those are the relative maximums and relative minimum values respectively. And so I don't really even need calculus to do that, but I'm going to show you how the calculus does relate to that by taking a look at the first derivative here. That when I do turn that on, notice that graph is above the x-axis to the left of -2. And notice that the maximum is at -2. And notice to the left of -2, the graph is increasing. And so that's what we said, was the relationship of the first derivative with its graph, that wherever the first derivative is positive, right, that would be to the left of -2, right? This blue graph is positive to the left of -2. The red graph is going to be increasing in that same interval, which in this case is to the left of -2. Okay. And then when I get to this point, now remember, don't get mixed up with this. I'll just turn that off here for a second. I think I could turn that point off. Turn off the label also. Notice, where this graph is below the x-axis, which would be in between -2 and 3, notice the function is decreasing between -2 and -3. And then I should say -2 and 3. And then at 3, it actually goes back to, once I'm beyond 3, it goes back to increasing again. And notice this graph is above the x-axis to the right of 3. So essentially, wherever the blue graph is above the x-axis, it is going to be, that indicates the first derivative is positive, and therefore the graph is going to be increasing. And you can see that here as I trace, notice, if I'm going to be anywhere between or to the left of -3, notice that first derivative is positive. And I'm just focus right here on this value here. When I get to -2, I'm sorry, -3, excuse me. Oh, where's that max? Oh gosh, -2. Yeah, I said it right the first time. If I get it -2, notice that it's equal to 0. Okay. And so this is telling me the slope of the tangent at -2 is equal to 0. And sure enough, if I did draw a tangent line in here, I'd have a horizontal tangent. And then as I continue on here, notice now I'm going to get all negative values up until I get to the point where x is equal to 3, and it should be equal to 0 again. And sure enough, it is. But anything between -2 and -3, notice I'm always going to get a negative value here for my first derivative. So that's just punching into the function. And then when I get back to the right of 3, notice I again have some positive values here. Okay, so now I'm going to turn that label on, turn the point on. As I trace, we can see it as it comes back down here. And I have the point slope form of the knot line here. Okay, so this is going to draw the tangent line. The reason why it's going to be the tangent line is that y minus y1 and x minus x1, in this case a, okay, and f of a are going to be points on that line, and the slope is going to be constantly changing based on wherever we are on that function to have the slope of the tangent. So essentially what I turn this graph on, notice it's going to graph a tangent line now, okay? So again, you can see that that slope of that green line is positive up until the point where I get to -2, then it's 0, okay? You can see the slope 0 right here, and it appears to be a horizontal line. And then now that slope goes back to negative wherever the graph is decreasing, okay? And again, when I get to 3, notice it's 0 again. And notice on that whole interval, again, that's where the blue graph was below the x-axis, which would indicate the first derivative is equal to or less than 0. And then I go back over here and go to the right, I go back to positive values again. Okay, now that's the first derivative, okay? What about the second derivative? Well, I can graph that function as well. And remember, the first derivative or second derivative is just the derivative of the first derivative. So if this were my original function, this is just going to tell me where this function is increasing and decreasing, okay? And that in itself is going to tell me something about concavity, okay? Now, as I look at this red graph here, all right, I'm going to turn off the slope in the first derivative for a second here. Notice that when I get to about 0.5, okay, when I'm right at 0.5, notice that's where the second derivative is less than 0. And remember, where the second derivative is less than 0, that's where it's concave down. So when I get here at about 0.5 on my graph, I'll tell you what I'll try to do is I'll try to get the point A here. Let me get over here at 0.5. Okay. When I'm at 0.5, right at this point right here, I'll turn this one on as well. That is going to be, it kind of looks like where it goes from concave down to concave up, and that's our inflection point. And notice when I'm at 0.5, the second derivative is equal to 0. So wherever this orange graph is below the x-axis, that tells me the second derivative is less than 0 or negative, and that tells me that's the interval in which it's concave down. Then when I get to the right of 0.5, say if I scroll over from that point on, notice that I'm going to be concave up when I go to the right of 0.5. The graph is above the x-axis. The orange graph, that tells me my second derivative is greater than 0. And here, you can see that that's the case. My second derivative is greater than 0. And notice, again, that's where the graph is concave up. And when I'm right at 0.5, let's see if I can back up and stop right there. When I'm right at 0.5, that appears to be where second derivative is equal to 0, or it is where it's equal to 0, and that's where the graph changes concavity from being concave down, concave up, which is, again, we know is a point of inflection, okay? So, that's how those graphs relate to one another. Just a thing to keep in mind here that if I look on that interval, and I'm going to scroll all the way over here, and when I go up, starting from -9 up until 0.5, if you could tell me what's happening with these numbers right here, what seems to be happening? I'm starting at 91, and I'm going continually, it looks like I'm going continually down, right? And so if I asked you what's happening to the first derivative, I think you would have to say that it keeps getting smaller and smaller and smaller and decreasing. even when I go beyond that, those numbers are keep getting smaller and smaller and smaller and smaller and smaller. And when I get at that magic number of 0.5, okay, notice it continually got smaller till I get to negative 6.25. But notice what starts happening to the right of it. Now they're getting it increased a little bit, and it's increasing. Now it's going back up, right? Those numbers are getting larger, right? Those numbers continually getting greater than the one previous to it and keep getting larger and larger and larger and larger, okay? So that again, the second derivative tells what's happening in the first derivative. It's getting smaller and smaller and smaller. It's decreasing, right? And if you look at what the tangent line looks like now, what's happening to it? Well, the tangent line is still positive, right? Still positive, but it's getting smaller. Right here, it's 0, but it's still getting smaller, right? The slope of the tangent is 0. Now it again keeps getting smaller and smaller and smaller and smaller and smaller, right until when I get to that point, 0.5, then what's going to start happening with the slope of that tangent? You can see that it was a big positive number, went to 0. Now it's just getting a little bit bigger and bigger, but negative number, it's still going down. Now, once I get past 0.5 here, you get past it, now what's happening in the slope? Well, that green line starts to increase, right? Those slopes, even though they're negative, they're getting to be larger and larger, larger values. And there we go. Okay. And so now you can see that the graph, that first derivative keeps going up and it's going to continue increasing, which would tell us again, that means that that graph is going to be concave up. Okay. Why? Because your second derivative again is positive for anything to the right of 0.5. So kind of a dynamic point of view here. Like I said, I turned off that other derivative. I can turn it back on now. How about if I turn on the right function? But kind of looks a little confusing here with all these graphs on at one time, but I've analyzed them, with the first and second derivative. And again, if we were just looking and I turned off the tangent line and even turned off this point A, I can always use these graphs. In other words, I can use the blue graph, the first derivative, to analyze what's happening to the red graph, the original function, as well as using the orange graph to analyze what's happening to this red function. Why? Because this function tells where the graph is increasing and decreasing, right? And we can also use it to tell where it reaches a local max or a local min, just by examining what its derivative is equal to. And then this graph tells us where the graph is concave up and concave down and where it changes concavity at that inflection point. All right. So a lot going on there. I think what I'll do is I'll even post this link to the right below the video and the announcements so that you have that as a resource. And that's it for this video. It's just a big idea video explaining what the relationship between a function and its first and second derivatives.